Every Mosquito built had 30,000 brass screws holding the wood together. Every Mosquito built had a pair of Merlin engines bolted to it, set by Rolls-Royce to a certified maximum of plus 18 pounds of boost. And every Mosquito of 105 Squadron between November 1942 and the end of the war had its boost surreptitiously cranked up to plus 20, a setting that exceeded the certified limit, by a man named Roderick Banks, who was court-martialed, penalised, and then promoted. The performance advantage that defined the Mosquito's wartime reputation, its ability to outrun every German interceptor, wasn't an inherent property of the airframe. It was the work of one senior engineering officer who decided the manual was wrong and acted on that assessment without permission, in a hangar, at night, without paperwork. The paperwork caught up eventually. So did the punishment. And after the punishment came something the official record has never explicitly named. RAF Marham sits on flat Norfolk agricultural land, about 15 miles southeast of King's Lynn, close enough to the Wash that east winds carry salt off the mudflats. In autumn and early winter, it gets dark early and stays dark, cloud pressing low across fenland that's barely above sea level. The kind of landscape where you can see an aircraft approaching from 5 miles out, because there's nothing between you and the horizon to interrupt the sightline. On September 29, 1942, number 105 Squadron moved there from RAF Horsham St Faith, bringing their de Havilland Mosquito B-4s, twin-engined bombers built from Canadian birch plywood, balsa wood and Sitka spruce, assembled with the enumerated count of 30,000 brass screws per airframe, 2 men in a cockpit that sat over the nose like a greenhouse, and no guns anywhere on the aircraft. The silence of those airframes was deliberate and deeply contested. The Mosquito carried no dorsal turret, no ventral position, no tail gunner, no 303 Browning machine guns in the wings. None. The design premise, one of the most contentious concepts in British pre-war aviation procurement, held that an unarmed bomber would survive over occupied Europe in daylight through speed alone, and that the weight saved by eliminating defensive armament could be converted directly into the performance margin that made defence unnecessary. The Air Ministry had argued both sides of this proposition simultaneously through the late 1930s. Speed was insufficient insurance without guns, but the guns added weight that reduced the speed that was supposed to be the real insurance. The debate was still running when war started. The Mosquito was built anyway. 105 Squadron received the first operational Mosquito B-4 at RAF Swanton Morley on November 15, 1941. Their first combat mission went out on 31st of May 1942. 6 months of working up on an aircraft the RAF had never operated before, developing navigation techniques, low-level approach profiles, and bomb release parameters that the aircraft's speed demanded, rather than those inherited from the Blenheim and Hampton crews who formed the core of the squadron's pre-Mosquito experience. A typical 2-group low-level mission in this period started before dawn with a briefing in a drafty Nissen hut, a handwritten target map, weather reports from Mosquito Met flights that had gone out before first light to check the cloud base over the target area. The 2-man crews, pilot and navigator, flew their approach below the cloud cover, if there was any, or flat across the landscape, if there wasn't, at altitudes low enough that the throttle settings needed for evasion were the same settings that created genuine bird strike risk on the windscreen. They dropped their bombs at relatively low altitude and turned for home before German fighter controllers could respond effectively. The entire effectiveness of the operation depended on the premise that no fighter could catch a Mosquito that didn't want to be caught. By late 1942, that premise was being tested in specific ways that the operational record was starting to document. 139 Squadron moved to Marham alongside 105 in October 1942, joining the low-level daylight precision bombing assignment that No. 2 Group had designed around what both squadrons were supposed to be. The combined schedule was demanding. Specific industrial and transport targets, in daylight, below the cloud base, without fighter escort, at altitudes where the aircraft were close enough to the Dutch and German countryside that birds were a genuine hazard rather than a background presence. That last detail isn't incidental. It quantifies exactly how low they were operating. Birds don't cruise at 3,000 feet. The aircraft illustrating the gaps in the design premise most precisely was the Focke-Wulf FW-190 AJG-26, the Abbeville wing, one of the Luftwaffe's most experienced fighter units, had introduced it over northern France in late 1941, and by 1942 it was the standard day fighter across occupied Western Europe. The A3 and A4 variants, operational through 1942 and 1943, were formidable at low and medium altitude. Fast, stable gun platforms powered by the BMW 801 radial, capable of putting 20mm cannon rounds into an aircraft at ranges that earlier German fighter types had found technically demanding. Flown by men who'd been accumulating combat hours since the Battle of France. The aircraft had one structural limitation the Mosquito's crews understood, and the FW-190 pilots understood equally well. Above approximately 20,000 feet, the BMW 801's performance degraded sharply without the two-stage supercharger configuration that later German fighters would carry. The FW-190A was a medium-altitude weapon, designed to fight below its performance ceiling rather than to chase targets into thinner air above it. At 18,000 feet, with both aircraft in their respective performance bands, the margin was close enough to feel in the cockpit. On 29th of August 1942, 6 weeks before 105 Squadron moved to Marham, a formation of their Mosquitoes attacked the Pont-à-Vendin power station in northern France. FW-190 fighters intercepted them head-on and swung around to attack from the stern. The Mosquitoes used their speed advantage to pull clear. They got home. The word the after-action reporting used was outpace, accurate and insufficient. It described a margin rather than a comfortable result, and pilots who'd been through the engagement knew the difference between winning a race by a second and winning it by enough to not have to think about it. October brought harder specifics. On the 20th, Mosquito B4 serial DZ313 departed Marham on a cloud cover raid against Hanover. Cloud cover attacks used overcast as concealment, approach under cloud, break into clear air for the bomb run, disappear again before fighter controllers could position an interceptor. DZ313 didn't return. The pilot, Flight Sergeant Lawrence Walter Death of the RAF VR, was killed. His observer, Warrant Officer Frank Edward Malcolm Hicks, was killed. No cause of loss was established in the available documentation. 10 days later, on the 30th, Mosquito DK316 flew a low-level daylight raid against the Lingen-Ems industrial complex in northwestern Germany. Anti-aircraft fire brought it down at 14:20 hours local time. It crashed at Californiastraat in Den Helder on the Dutch coast. Both crew members died. 2 aircraft, 4 men. A squadron running 8 to 10 operational Mosquitoes at any time had just lost a substantial fraction of its frontline strength in 10 days to 2 different threats, one with no established cause One to the anti-aircraft coverage that low-level daylight raiding inevitably attracted when the routing took the aircraft over defended positions on a predictable line of approach. Wing Commander Huey Idwal Edwards, who commanded 105 Squadron, wasn't given to caution as a personal disposition. He'd received the Victoria Cross in July 1941 for leading a low-level attack on the port of Bremen through severe flak and fighter opposition, pressing the attack despite losing aircraft from his formation before reaching the target. He demonstrated on that mission that he would accept serious losses to achieve a result. When he registered concern about the loss pattern at Marham through that autumn, it wasn't the anxiety of a cautious man. It was the arithmetic of a decorated combat leader who knew what the numbers were saying and was prepared to say it to the Air Ministry directly. The raid that crystallized the operational situation was Operation Oyster, flown on December 6, 1942. The target was the Philips electrical and radio manufacturing complex at Eindhoven in the Netherlands, producing radio valves and electronic components for German industry since the occupation. The timing on a Sunday was deliberate, intended to minimize Dutch civilian casualties on the factory floor. Edwards led the Mosquito element, 8 aircraft from 105, 2 from 139, alongside Bostons and Venturas from other 2 group units. The Phillips works were substantially damaged. 14 aircraft from the combined formation were lost. 23 aircraft returned with bird strike damage embedded in their airframes. Impacts sustained during the low-level approach across the Dutch countryside at altitudes where the hedgerows were visible from eye level through the cockpit glass, and the aircraft's shadow crossed the fields beneath them at 380 miles per hour. The Mosquito element survived. Speed and routing carried them through. But the pattern developing across that autumn was precise about what it was recording. The margin between arriving and not arriving was narrow enough that improvements to the margin mattered. That was the situation Banks came to Marham to address. Francis Rodwell Banks was known in every professional setting by the nickname derived from his middle name, Rod. The name Roderick, which appears persistently in popular accounts of this story, entered secondary literature as a compression of Rodwell and embedded itself there without correction. His confirmed name across every available bibliographic record was Francis Rodwell Banks, Air Commodore, Honorary Fellow of the Royal Aeronautical Society, and the officer identified in a wartime Cambridge Aeronautical Journal citation as Director of Engine Production, Rod Banks. That title is essential to understanding what he did at Marham. Director of Engine Production is the office where Rolls-Royce's engineering capability met operational requirements, where decisions about engine configurations, modification authorizations, and performance certification had real consequences for the aircraft squadrons flew that morning. Banks had reached that position through 6 decades of work on internal combustion engines, in 3 categories he himself would later list, with the flat effect of a parts inventory, as marine diesels, automobile engines, and aero engines. The Royal Aeronautical Society's record of his wartime contribution describes him as having been headhunted by the RAF at the conflict's start and tasked with supervising engine development work. The Cambridge Journal documentation places him specifically working on a standardized Merlin power plant for the Bristol Beaufighter, a project that required understanding not what a Merlin produced against a calibrated test rig in Derby, but what it did under operational conditions. Cold air at altitude, power settings sustained over hours rather than minutes, a pilot who needed the machine to keep working. Banks had never been a comfortable institutional presence. The evidence for this is the book he published in 1978, nearly a decade after he retired from engineering. He called it "I Kept No Diary: 60 Years with Marine Diesels, Automobile and Aero Engines", published by Airlife Publications in Shrewsbury. 247 pages, hardback, ISBN 0950454397. The United States Air Force Office of Air Force History placed it in their 1984 annotated bibliography of aeronautical literature, alongside primary sources and serious technical histories, not in the popular aviation section. The title is a joke with a specific architecture. A man announces he kept no record of anything, then fills 247 pages with everything he remembered across 6 decades of engineering. The subtitle lists marine diesels before aircraft engines, catalogued with the effect of a stockroom inventory, because that's the chronological order, and he saw no reason to arrange it otherwise. Banks's relationship with official records, what they said, what they didn't say, and the gap between the two, is present in the title before the reader opens the cover. That relationship was about to become professionally relevant in spring 1943 in a way Banks couldn't yet have predicted when he reached Marham in November 1942. He arrived to engines being operated at a fraction of what they could physically deliver. The Rolls-Royce Merlin ran on a supercharged fuel-air mixture, and understanding what Banks did in 105 Squadron's hangar requires understanding what the supercharger was enforcing, and why that number mattered enough to enforce at all. At sea level, atmospheric pressure provides approximately 14.7 pounds per square inch to fill an engine's cylinders on each intake stroke. An unsupercharged engine is bounded by that ceiling, its power output determined by how much air the atmosphere can push into the cylinders naturally, which is why piston engines lose power as they climb. The Merlin's supercharger, a centrifugal compressor driven mechanically by the crankshaft through a gear train, forced air into the intake manifold at pressures substantially above what the atmosphere could naturally provide. It was lying to the engine about what altitude it was operating at, telling the combustion system it was at sea level when the aircraft was at 15,000 feet. More air meant more fuel burned per stroke, more energy released per combustion event, more power to the propeller, more speed at altitude. The supercharger wasn't optional equipment bolted on as an afterthought. It was the fundamental reason the Merlin could take an aircraft to combat altitude and still have enough left to be useful there. Boost pressure, the measurement of how much the supercharger raised manifold pressure above standard atmospheric, was the dial on how much of that capability the engine was authorized to use. The boost limit wasn't bureaucratic caution, it was chemistry. When a fuel-air mixture inside a cylinder is compressed beyond a threshold defined by the fuel's octane rating, it ignites spontaneously before the spark plug fires. This is detonation. Combustion triggered by compression rather than by the timed spark, releasing energy as a shock wave rather than a controlled burn that pushes the piston down the cylinder in the design sequence. Stanley Hooker, who ran Rolls-Royce's supercharger development group through the war and whose autobiography, Not Much of an Engineer, became one of the essential technical memoirs of the period, described what happened to a detonating engine with precision. It could literally hammer small holes in the cylinder head and pistons. That's the physical mechanism. Shock waves from premature ignition struck alloy surfaces at frequencies the metal wasn't designed to absorb, each event adding microscopic damage that accumulated toward catastrophic failure. An automobile engine detonating mildly produces a knock, an inconvenience, a signal to use better fuel next time. An aircraft engine detonating at emergency power settings over Germany didn't produce a knock. Within minutes, it produced an engine that had destroyed its own pistons from the inside. At operational altitude, with 2 crew and no defensive armament and nowhere to divert, that wasn't a maintenance problem. It was the end of everything. The octane rating of aviation fuel determined where that threshold sat. Lower octane fuel began detonating at relatively modest boost levels, around plus 6 pounds per square inch by period engineering estimates for 87 grade fuel. Higher octane fuel resisted pre-ignition more effectively, tolerating higher compression before the same physics asserted themselves. Fighter Command had begun converting its Merlin-powered aircraft to 100-octane fuel in March 1940, drawing on supplies from American refineries shipped across the Atlantic in convoy through the U-boat campaign. By the end of 1942, approximately 640,000 tons of 100-octane aviation petrol had moved through the British distribution system. From marine terminals at Thames Haven east of London, Stanlow near Liverpool on the Mersey, and Avonmouth on the Bristol Channel, through aviation fuel distributing depots by rail and pipeline, and out to RAF stations including Marham by 2,000-gallon road tankers that refueled the Mosquitoes each morning. The aircraft 105 Squadron, launched in autumn 1942, were running 100-octane petrol, with a knock resistance substantially higher than the boost limits printed in the Merlin operating manual had assumed when those limits were first certified. The Merlin 25, fitted to 105 Squadron's B4s, used a single-stage 2-speed supercharger, one compressor driven at 2 gear ratios depending on altitude, giving the engine more useful performance across a range of heights than a fixed ratio design could have provided. The certified boost limit for these engines stood at plus 18 pounds per square inch. Banks believed the headroom existed to push 2 to 3 pounds beyond that figure against the fuel now available, and acted on that calculation. His reasoning was grounded. The 100-octane fuel already sitting in the Mosquito's wing tanks had a detonation resistance substantially above what plus 18 boost required of it. The supercharger hardware could physically generate higher manifold pressure than the certified limit permitted. The gap between the hardware's capability and its authorized operating range was real and measurable from engineering knowledge without needing a formal test program to confirm it. The limit had been set against fuel grades and engineering assumptions from an earlier period of the war. The fuel had moved on. The certified limit hadn't. Men from 105 Squadron were dying, at least in part, in the space between those two facts. Banks resolved to close that space with tools he knew how to use, rather than a memorandum and an approval cycle that would run months while the loss columns kept filling. The Merlin's boost pressure wasn't maintained by the pilot's hand on the throttle. An automatic device called the Boost Control Unit held it, a pressure-sensing mechanism mounted in the engine bay that monitored manifold pressure continuously and adjusted the throttle butterfly valve to maintain a fixed reference pressure regardless of altitude, temperature, or engine speed changes. When the aircraft climbed and atmospheric pressure dropped, the boost controller opened the throttle to compensate, maintaining the target pressure. When temperature varied, the controller corrected. The device was a continuous regulatory system whose entire function was to hold one number constant: the target manifold pressure it had been calibrated to maintain. That reference was set by a mechanical arrangement inside the controller, a pressure-sensing capsule whose response was determined by a calibrated spring. Adjusting that spring's load, or the capsule's reference position, shifted the target pressure the controller worked to maintain. This was a documented adjustment, performed routinely at certified settings during scheduled overhauls by any competent Merlin engineer. Performing it to a non-certified setting, above the authorized operating range, required exactly the same physical access, the same tools, the same knowledge of the controller's internal geometry. The difference was the reference value being set, and whether the engineer doing the setting had authorization to set it there. Banks didn't have authorization. He had the knowledge, the access, and the calculation that told him the modified setting wouldn't destroy the engines. Picture the hangar at Marham after midnight. The maintenance crew working under fluorescent tubes that cast hard shadows across the engine nacelles. The airfield's perimeter lights were blacked out. Wartime Britain ran dark, and the only illumination came from what the maintenance crew generated inside the building. A Mosquito B-4 sat on its undercarriage with its cowlings open, both Merlins exposed, the cockpit dark and empty above them. Reaching the boost controller required climbing up to the engine nacelle with appropriate tools, locating the mechanism in the bay, and getting hands on the internal components without disturbing anything else in the cramped space around it. The adjustment itself was precise work. Too much movement on the spring reference, and the engine would eventually reach its detonation threshold, regardless of the 100-octane fuel's resistance. Too little, and the performance gain was marginal relative to the risk being accepted. Banks knew what the controller looked like from inside, the way a surgeon knows an incision line, with the specific confidence of someone who has done the same procedure repeatedly in conditions where getting it wrong wasn't recoverable. Both Merlins on each aircraft needed identical adjustment. Mismatched boost settings at the power levels Banks was targeting would have produced asymmetric thrust, detectable in handling and potentially dangerous at the critical moments of takeoff and steep climbing turns. Matched settings on both engines gave an aircraft that handled identically to any other Mosquito in the squadron, flew normally in formation, and went through the same pre-mission checks with the same instrument readings, while achieving a speed that no version of the Mosquito B-4 had official clearance to reach. The work required approximately 18 hours per engine. The concealment was built into the method, RAF. Maintenance documentation flowed through the Form 700, the aircraft's engineering record, the legal account of everything done to His Majesty's aircraft. Night work performed without generating Form 700 entries left no trace in the official maintenance record. The aircraft's documentation showed standard engines maintained to standard specifications. The engines weren't standard. An inspector working from the paperwork would find nothing out of order. An inspector with the engine cowlings open and the boost controller's internal components exposed would find something entirely different. That second inspector arrived in spring 1943. Before that, Banks's modified Mosquitoes went to war. The standard Mosquito B-4 at operational altitude flew at approximately 380 to 388 miles per hour in clean configuration, the variation reflecting different loading conditions and measurement approaches, rather than fundamental disagreement about the aircraft's capability. The AAEE performance trials at Boscombe Down provided the authoritative speed data under controlled conditions. Operational figures from actual sorties produced a slightly different distribution, reflecting combat weight, fuel state, and atmospheric variation. These were the numbers the manual described and authorized. Banks's modification, based on the operational records covering the period of its use, increased that speed by approximately 25 to 30 miles per hour. Against a baseline of 380, That puts the modified aircraft somewhere around 405 to 410 miles per hour at altitude. The significance of that figure lay not in the absolute number, but in what it meant relative to the aircraft that had been catching up. At 18,000 feet, near the upper edge of the FW-190A's effective performance band, and the altitude at which the Merlin 25's single-stage supercharger delivered its best combination of power and economy, the FW-190A3 and A4 were capable interceptors. The BMW 801 was in its designed operating range below 20,000 feet. An FW-190 pilot, positioned above a standard Mosquito, with altitude advantage and a favourable intercept angle, could press an engagement through to a firing solution. An FW-190 pilot, chasing a modified Mosquito at 18,000 feet, was pursuing something that was pulling away from him into the altitude band where his own aircraft's advantage steadily dissolved. The difference wasn't speed alone. It was where the geometry of the engagement was decided before it began. The loss rate differential is the operational verdict on all of that. Modified aircraft operated at a loss rate of approximately 0.33% per sortie, against 0.6% for standard configuration. Both figures sound small in isolation. As a proportion, 0.33 against 0.6 is barely over half. Across hundreds of operations through 1943 and into 1944, that difference represents crews who came back from missions that, at standard boost, they might not have. Banks couldn't have calculated that differential in November 1942. He had the engineering knowledge to predict the speed improvement and enough operational awareness to understand what speed at the right altitude meant for men flying unarmed aircraft into Germany without escort. On January 30th, 1943, the operational value of each additional mile per hour was demonstrated against a target chosen specifically for its political visibility. 3 Mosquito B-4s from 105 Squadron took off with a specific brief. Reach the main Berlin broadcasting station at precisely 11 o'clock in the morning, while Reichsmarschall Hermann Göring addressed a parade marking the 10th anniversary of the Nazi government's coming to power. The mission timing had been planned around the anniversary schedule with considerable precision. Göring was due to speak at 11. The Mosquitoes were due over the target at 11. The 3 aircraft from 105 Squadron reached the broadcasting station at 11 o'clock. They bombed it at the planned minute. Göring was kept off the air for more than an hour. The mission had been designed around the spectacle as much as the physical damage. 3 bombers arriving at the Reich's capital on a schedule announced before takeoff, hitting a specific building at a specific time, in weather that made the operation demanding rather than routine, against a city whose air defences had been positioned by a command structure that had accepted Göring's own assessment that daylight Mosquito raids on Berlin weren't operationally viable. That afternoon, a second formation from 139 Squadron followed, with an identical brief, against the Sports Palace in the Wilhelmstrasse district, where Goebbels was scheduled to address a rally. That formation also reached Berlin at the planned time, and bombed at the planned minute. 1 aircraft from the afternoon raid was shot down by anti-aircraft fire over the capital. Berlin's flak defences were dense and well supplied, even when its fighter coverage had failed to intercept, and the crew were killed. The rest turned for Norfolk and came home. Berlin's air defences had been told by their own command structure that a Mosquito attack on the capital in daylight was impossible. 105 and 139 squadrons had not merely demonstrated it was possible, they demonstrated it on a published schedule, at targets chosen for maximum political visibility, with the navigation precision to hit specific buildings at specific minutes over the most defended city in Europe. 6 weeks after the Berlin raids, Goering addressed German aircraft manufacturers and told them the Mosquito made him furious. It turned him, he said, green and yellow with envy. He observed that the British had chosen to build their most effective bomber from wood, had enlisted piano factories to assemble it, and had kept increasing its speed beyond what the Luftwaffe's fighters could match. He called the engineers responsible geniuses. As technical assessments from senior figures on either side went, this one was more accurate than most. Spring 1943. A Rolls-Royce inspection team arrived at RAF Marham for what the maintenance schedule classified as routine technical review of the squadron's Merlin 25 engines. Rolls-Royce maintained oversight responsibility for engines in operational aircraft, periodic physical inspection of hardware rather than mere review of paperwork. An inspector examining the boost control systems of at least some of 105 Squadron's Mosquito Merlins found internal configurations that matched no authorized setting for any production variant of the Merlin 25 in any documentation held by the manufacturer. The charge against Banks was specific: unauthorized modification of His Majesty's aircraft, made without authorization from Rolls-Royce, made without authorization from the Air Ministry's Technical Directorate, and, this element made the charge considerably worse, made with no record whatsoever in the maintenance documentation. Under RAF maintenance regulations, an absence of paperwork for an aircraft modification carried a particular implication. An engineer who adjusts an engine component and fails to document it commits a procedural error. An engineer who adjusts an engine component then operates the aircraft on operational missions over enemy territory without any documentation of the adjustment has demonstrated that he understood the modification wasn't permitted and proceeded regardless. The empty Form 700 entries were evidence of deliberate concealment, not forgetfulness. Banks had performed this operation on multiple engines, across multiple aircraft, over multiple months. What specifically followed requires an honest statement of what the available record establishes and what remains contested. Banks, in his own memoir, reportedly described the proceeding using the word court-martial. That term carries legal precision under the Air Force Act 1939. A formal RAF court-martial required a convening authority, a board of officers with a wing commander as president, formal charges and response, procedural rights for the accused, and a recorded finding. The resulting record would sit in the National Archives under AIR 18. The series covering RAF courts-martial from 1941, searchable by surname. The RAF historian of 105 Squadron has described the proceeding differently, as an internal disciplinary action that didn't reach the statutory court-martial threshold. Under RAF regulations, a commanding officer could impose significant punishment for certain classes of offence through a process that left a lighter documentary trail than a full statutory court-martial. Both accounts can't simultaneously be accurate. What Banks wrote in his own words and what the AIR 18 registers at Kew actually contain under his name would resolve the question. Those sources are accessible to researchers. They haven't been reconciled into a single settled public account. This script uses the word court-martial because that's the framing Banks apparently applied to it, and because the archival path to a more precise characterization remains open rather than closed. What isn't contested across any version of events is this. An adverse finding of some kind was made. Banks was penalised, and the modification was an offence under the regulations that governed his work. The charge wasn't about outcomes, it was about authority. His engines hadn't destroyed themselves. His aircraft had returned from missions that aircraft with standard engines hadn't always returned from. Goering had been kept off the radio, while his own FW-190s couldn't catch the Mosquitoes that did it. None of that constituted a defence, because the charge sheet didn't include a category called "The engineering calculation was correct." It included a category called "The modification was unauthorized," and Banks had absolutely, unambiguously, and documented by the physical evidence of the boost controllers themselves, made an unauthorized modification while deliberately concealing that he'd done so. He had nothing to offer the proceeding that its framework could accept as mitigation. He'd known that when he decided to do it anyway. Banks didn't leave operational engineering after the proceeding. His documented wartime record shows continuous senior service through the remainder of the conflict. The Cambridge Aeronautical Journal's wartime citation places him as Director of Engine Production during the period from late 1943 through 1944. The years when the progressive increase in certified Merlin boost limits was systematically transforming the performance profile of every aircraft in RAF service. Popular accounts of this episode describe Banks as being quietly rehired within weeks to do precisely what he'd been penalised for doing, but this time with official sanction, by something called the Air Ministry Special Duties Branch. The specific branch name can't be confirmed from available sources as an engineering authorization body with that designation. The RAF's Special Duties label in wartime primarily attached to the secret air transport units, 138 and 161 squadrons at RAF Tempsford, supporting resistance operations across occupied Europe, a function quite different from engine certification. What can be confirmed is that Banks's career continued in a senior engineering capacity, that his job title placed him at the intersection where Rolls-Royce's development work met Air Ministry procurement policy, and that the Air Ministry's position on Merlin boost limits moved in one consistent direction through 1943 and 1944. Whether the mechanism of that continuation was a formal transfer under a specific authorization scheme, or simply the survival of a career that the adverse finding hadn't permanently terminated, is unclear from the documentary record currently accessible. The progressive history of the Merlin's certified operating limits tells the institutional story without requiring that mechanism to be precisely identified. The Merlin 45, powering later Spitfire variants from 1941, ran at higher boost settings than the original Merlin marks used in the Battle of Britain. The Merlin 66, entering service in 1943, carried further increases. The Merlin 70 series was cleared to operate at plus 25 pounds of boost, substantially above the figure that had applied to 105 Squadron's aircraft when Banks arrived at Marham. The Mosquito B Mark 16, which entered Squadron service in February 1944, with Merlin 72 and 76 engines rated at 1,680 and 1,710 horsepower respectively, achieved a maximum speed of 415 miles per hour at 28,000 feet. Certified, official, written into the type specification, completely dependent on the principle that 100-octane fuel and improved engineering confidence could sustain boost pressures far above what the earlier conservative limits had allowed. Stanley Hooker's supercharger team at Derby had been pursuing the same performance headroom through authorized channels throughout this period. The March 1941 internal Rolls-Royce report, prepared by Hooker, Harry Reid and Alan Yarker, released publicly by the Rolls-Royce Heritage Trust in 1997, documents serious altitude performance characterization work underway at Derby long before Banks reached Marham. Rolls-Royce's engineers weren't ignorant of the headroom the 100-octane fuel was providing. They were working through it on a schedule set by the development and certification process, rather than by the loss rates of specific operational squadrons. Whether what Banks demonstrated at Marham, in the mission completions, the declining casualty figures, the Berlin raids flown on schedule, accelerated the Air Ministry's urgency around that certification process, is a question the correspondence between Bomber Command's operational experience and Derby's engineering timeline could answer. That correspondence sits partly in archives that remain partially restricted, and partly in the Rolls-Royce Heritage Trust's holdings. The answer isn't publicly assembled. What is publicly assembled is the outcome. Every variant of the Merlin certified for operational use through 1944 was running boost pressures that would have been called unauthorized at Marham in November 1942. Each progressive certification validated without naming it the argument Banks had made without authorization from a hangar in Norfolk. Beatrice Schilling had worked from a structurally similar position roughly a year before Banks, starting from lower in the institutional hierarchy. A precision engineer at the Royal Aircraft Establishment at Farnborough, and a competitive motorcycle racer who held a Brooklands Gold Star for lapping the circuit at over 100 miles per hour. Schilling identified in 1940 and 1941 why Spitfire and Hurricane pilots were losing engagements against Bf-109s in circumstances that seemed aerodynamically straightforward. The Merlin's float-type carburetor supplied fuel using a mechanism that depended on gravity. Under positive G, the float sat correctly and the fuel fed properly. Under negative G, when a pilot pushed forward into a dive to evade an attacker or press through to a target, the fuel floated away from the float mechanism, the carburetor starved, and the engine cut out for several seconds. The Daimler-Benz direct injection system in the Bf-109 was indifferent to which direction gravity pointed. A German pilot could dive away from any pursuing Spitfire and watch the Merlin choke itself silent. Schilling designed a restrictor disc, a brass plate with a calibrated orifice drilled through the centre that could be fitted to the carburetor intake in the field without dismantling the engine, limiting fuel flow enough to prevent starvation under brief negative G. Pilots named it Miss Schilling's orifice, which was accurate. Affectionate in the way combat pilots are affectionate, and slightly indecorous, which is probably why the name lasted. The disc was deployed across Fighter Command as an urgent interim solution, while the proper carburetor redesign worked through formal development and certification, a process that eventually produced the Bendix-Stromberg pressure carburetor as the permanent fix. The structural parallel to Banks's situation is near exact. Individual engineer, identified performance gap, solution deployed faster than the certification machinery was designed to accommodate, immediate operational benefit, eventual official adoption. What Schilling had that Banks apparently didn't was the positioning to frame her intervention as an authorized interim measure rather than a covert one. The distinction between those two categories wasn't technical, it was institutional, and it determined whether the engineer in question ended up in the record as a contributor or as a defendant. Banks's memoir is the primary source this story needs most directly. I kept no diary. 60 years with marine diesels, automobile and aero engines. 1978, Airlife Publications, 247 pages, hardback. The USAF Office of Air Force History's 1984 annotated bibliography positioned it alongside primary sources and serious technical histories, not in the popular aviation category, but alongside material the Office of Air Force History considered worth citing precisely. What Banks wrote in those pages about the Marham modification, the inspection, the disciplinary proceeding, and the aftermath, his own words, in his own register, from the specific sensibility of a man who announced he'd kept no diary, while filling 247 pages with everything he'd remembered, is the account this episode has worked from at one remove. His memoir title is The Biographical Fact That Frames the Rest. Someone who understood the gap between official records and actual events, found that gap wryly amusing rather than troubling, and had spent 6 decades operating inside it. He reached Air Commodore. He was elected an honorary fellow of the Royal Aeronautical Society. He retired from engineering in 1971 after 60 years of internal combustion engines in 3 categories, having watched the institution that penalised him for exceeding the Merlin's certified boost limit progressively raise that limit until the figure he'd been punished for running became conservative by the standards of what Bomber Command was officially flying. His logbook, in one account, contained details of the Marham modifications in his own handwriting, and sat in an attic until 1996, 11 years after his death. That detail can't be confirmed from the available archival record. What can be confirmed is that he built the aircraft's speed advantage from a hangar floor at night without permission, and that the institution subsequently built the same advantage into every aircraft it operated, without mentioning him by name in any policy document currently accessible. The +20 modification Banks was penalised for in 1943 had, by the war's end, been exceeded by the certified boost limits of every major Merlin variant in RAF service. Nobody ever apologised. Subscribe for more stories like this.